once you will visit this team of PRC1 section B, you will get files folder, and in files folder you can download recordings. From Dr. Safir folder you can also download some PDF lectures and video lectures, and recordings normally we take online, and the lecture recorded is uploaded automatically. And in addition, in files folder you will also get so you will also get a folder of class materials, and inside that class materials I have uploaded lecture 1 introduction. I modified this file according to 2009 publication of ACI and the latest guideline about the concrete mix 214R, published in 2011. So some references have been modified in the introduction file, and one book is also uploaded here. If you will ask, I can also upload other soft books. So now the discussion will be on few left slides of introduction. You already have the recording of this introduction lecture uploaded by Dr. Safir. This ACI 318 2019 code be used for structural concrete. Now I want to talk about the design loads. So let me start recording of today's lecture. So at the moment 37 attendees are online. So that in order to design the structural members or reinforced concrete structures, you need to decide the loads. Dead load means self weight of the components, self weight of the structure, and it includes not self weight of the structural concrete, reinforced concrete, but also the superimposed load on that structure. For example, if you are calculating the load of RC slab, reinforced concrete slab, on top of it there may be some floor finish present, which is made up of plain cement concrete without any reinforcement inside. There is also a possibility on roof that some mud and roof tiles, or on intermediate floors some floor tiles, maybe clay tiles or marble tiles, are superimposed. So all of them which carry self weight will be considered superimposed load. So the loads which do not change their magnitude and position, they are static with respect to time within the life of structure, will be considered as the design dead loads. However, design live load means loads chiefly of occupancy. Those occupants which are using that structure, their self weight, their own load will be considered as live load in building structures, and in bridges, traffic load will be considered as the live load. So it is not permanent. It may be present or absent. They may be either fully or partially in place. A good example may be that in classrooms, in some cases, attendance or presence is 100%, and in some other cases, less students are sitting. So the live load will be reduced. Their magnitude and distribution at any given time is uncertain. We are given with some guidelines to decide the loads, not only self weights or dead loads, but also the occupancy loads. And on slide number 17, we have this summary of various materials, densities, and as well as intensity of the live loads. In first table, very important materials which are normally used in construction, their corresponding densities are summarized, and I recommend you to memorize them. For plain cement concrete, the density will be around 2300 kg per meter cube. And in reinforced concrete, where reinforcement is also present, the density will be little higher, and a good value is to be considered while estimating the self weights will be 2400 kg per meter cube. If brick masonry is present, stacking of bricks, the density proposed is 1930 kg per meter cube. While if sand or brick ballast or earth is present, then the good suggestion is around 1800 kg per meter cube. Normally, you will use these densities with the available thickness. So once you multiply the densities with their given thickness, for example, on roof slab, if earth or sand or brick ballast is present in a thickness of suppose 100 millimeter, then in order to get the uniform pressure on the slab, we will multiply this density 1800 kg per meter cube with 0.1 meter, which is equivalent to 100 millimeter, to get a pressure on roof slab of 180 kg per meter square. If the thickness of the ballast or earth present is 100 millimeter. So in this way, these densities are very useful, and we can convert them into pressure by multiplying the densities with their thickness. Or if we know the volume of the material, we can even multiply the density with volume to calculate the weight or load. And then in some cases, we need to convert that load into pressure. So again, then we need to divide that load with the influence area to convert it into pressure. So there will be some cases in your design task where you will convert the densities into pressures, while in some cases you may convert the density into load by multiplying it with volume. Then intensities of live loads are also summarized, and very commonly used values are given. In residential apartments, the live load normally used is 200 kg per meter square. So you will notice that here live load is summarized in terms of pressure, not in terms of density. And we will be using this pressure finally to determine the load on the structural members in terms of load per unit length, or if we want to convert it into a point load, we may multiply this pressure with area to get unit load. But live load, when you will consult different tables in different textbooks or in some codes, you will get the value in terms of pressure. Offices proposed live load ranges from 250 to 500 depending upon heavily loaded offices. Reading rooms 300, and heaviest here is the warehouses, go downs where there is heavy storage, and it increases to 1250 kg per meter square. So in this summary of occupancy load, heaviest is warehouse and relatively lightest is classroom or residential apartments or house. Now, more important is that how to design a structural component. And to design a structural component, question will arise that you want to design it against flexure, bending movement, shear, and torsion. So all these forces you want to resist in a structural member. Then the next question will be which method you will follow. Allowable stress design or ultimate, also named as LRFD, load and resistance factor design. So in all these design methodologies, the basic design equation will involve demand versus resistance, action versus reaction, load versus resistance. So if on one side there is applied action or demand, on other side is capacity. And if we equate them without considering some factor of safety, it might be dangerous. So what we do is we put a factor of safety in that equation. So either the demand may be exaggerated or the capacity may be reduced, or option is that both sides may get some factor of safety on demand side use a factor of safety greater than 1 because you want to amplify it. And on the resistance side, reduce the capacity and use factor of safety less than 1 because you want to get some reserve strength. So it means factor of safety means that you want to have more than desired capacity, design capacity, so that in case of some uncertainties, which are summarized underneath, uncertainty in assessment of the loads, uncertainty in terms of estimation of material strengths, poor workmanship at site, unpredictable or unexpected behavior of the structure, some thermal stresses or residual stresses can alter the demand, and also some imperfections in fabrication can change the cross sections and the demand as well, or can reduce the resistance. So in this way, factor of safety must be present whatsoever methodology, allowable stress or ultimate strength design you want to follow. The benefit of factor of safety is also that it will help you to fulfill serviceability requirements in structures. And serviceability requirement means that your deflections should not exceed a given limit. Deflections should not be excessive, and cracks, which are unavoidable, should remain hairline, invisible by naked eye. So such factor of safeties will help us in achieving such requirements. Factor of safety will also cover chances of natural disasters. So always keep in mind that the basic equation always is action demand should be equal to resistance, and either increase demand or decrease resistance, or take factor of safety on both sides, not only increase the demand but also decrease the resistance. So you will find that in ultimate stand design, the difference from allowable stress design will be, in allowable stress design, what will happen, you will not exaggerate the demand. At service loads, demand will be calculated, while the calculating the resistance, you will decrease the capacity. So factor of safety will be on side of internal resistance. You will lower down the stresses in the materials corresponding to the demand loads. So factor of safety will only appear on the right hand side of the equation. While in USD, what will happen, you will find that factor of safety will appear on both sides of the equations. You will increase the demand by multiplying the load with load factors, which will be more than one in most of the cases. 1.2 for dead load and 1.6 for live load. So loads you will increase by some factors, which are actually factor of safeties. While material strengths or resistance offered by the materials, you will reduce by bringing the factor of safety in the denominator, which is more than one, but once you will take reciprocal of it, or you will divide the resistance with a factor greater than one, it will reduce the resistance. So here what factor of safety is shown on this side. Once it will be brought to the left hand side, and keeping in mind that factor of safety means it is always greater than 1. So once this greater than 1 will come in denominator on the left hand side, it will reduce the material capacity, resistance offered. So this is how in USD design philosophy we will be writing our equations. And it is mentioned in first paragraph that strength design method is based on the philosophy of dividing factor of safety in such a way that bigger part of it is applied on loads and smaller part of it is applied on material strength. So qualitatively they are saying that FOS1 will be relatively bigger than FOS2, but both are actually playing their role in getting overall factor of safety, and in this way the structures or elements can be made more safer. So in our basic equations in USD, what you will find that in writing the equation, for example, if I am writing the equation for moment demand, for shear, or for axial force, I am making the demand of movement or shear or axial force bigger by multiplying them with load factors. And then I will put a subscript U to declare that these are ultimate demands, ultimate movement, ultimate shear, ultimate load. So 1.2 dead and 1.6 live will be multiplied with the self weight and with the live load respectively to get the ultimate demands. So dead load movement, if I am working on movement, I will say dead load movement, I will multiply it with 1.2, and live load movement, I will multiply it with 1.6 to get ultimate movement. And on the left hand side, material internally can resist that demand, and it will be abbreviated as M with subscript N, nominal resistance, nominal movement resistance, or nominal shear resistance, or nominal load resistance, which is without any reduction. But then, since I want to put factor of safety on the resistance side as well, I will also put a reduction factor which will be less than 1. And in this way, I am actually reducing the capacity, reducing the nominal capacity. So on the right hand side, factor increase the demand, and on the left hand side, factor reduce the capacity. So this is how USD equations are incorporating factor of safeties. ASD, allowable stress design, Dr. Safir will discuss in detail in his part of allowable stress design of structural members. However, on this slide number 21, what I can briefly explain is that you will find that in basic design equation, we are writing the demand as service load here without any factor of safety, while the resistance, capacity, material strength, we are reducing it by factor of safety. So this denominator, which will be more than 1, will reduce the resistance. And you will find that in material resistance, in ASD, we will use against service load, service demand, hardly 50% of the material strength. So in this picture, underneath, if in I talk qualitatively about concrete and steel, you will find that concrete hardly 45% of its peak, 45% of its maximum strength, 45% of its strength at the age of 28 days. So FC prime we determine by crushing two standard cured cylinders of size 150 millimeter dia by 300 millimeter height and cured according to ASTM specification for 28 days, and then at the age of 28 days we will crush them to find out what maximum strength they got, and that strength at the age of 28 days of standard cured cylinders will be declared as FC prime in ACI 318, building code requirements for structural concrete. And in allowable stress design, we will utilize against service loads hardly 45% of that FC prime. Although in this picture we are showing FC prime over 2, but once you will write the equation in ASD, you will write 0.45 FC prime will be the threshold which will be permissible in terms of stress when you are writing your capacity equations. While steel also will be stressed to hardly 50% of its yield strength at service loads in ASD when you are utilizing grade 300 and below steel. However, when you are using grade 420 steel, rather than Fy by 2, you will be further reducing the permissible stress in the steel to 40% of Fy, 0.4 Fy. So you will realize that full material capacity will not be used against service loads, but nearly half of it. It is important to note that in both allowable stress and ultimate strength design, analysis will be carried out in elastic range. Inelastic analysis will never be done. Analysis will be elastic. And in ASD, even the material strength which you are using is also almost in the elastic range. Strictly speaking, yes, steel has linear elastic behavior up to Fy, and we state that at half of its Fy, steel is linearly elastic, and our analysis is also elastic. However, concrete at its 45% of Fc prime will not be linearly elastic. It will develop some non-linearity. Very close to origin, it will be nearly straight stress-strain relationship, but once it will go beyond 0.2 or 0.3% of Fc prime, non-linearity will come in action. So analysis is elastic, and in ASD, material properties used are almost nearly elastic. However, in ultimate stand design, what will happen? You will be doing analysis elastic, but against calculated demand based on elastic analysis, you will exaggerate that demand by putting factor of safeties 1.2 dead, 1.6 live. So you will make that demand ultimate movement or shear or load, and then that ultimate demand you will use, and full material, like if concrete will soften here and it will get to this part after attaining post peak, 85% of its peak almost up to this branch, this full material strength of concrete and yield up to yield of steel. So up to this limit of concrete and steel, you will utilize in USD, not like ASD that 50, almost 50% of material in concrete. In USD, you will utilize full material capacities. So material in inelastic range, particularly concrete capacity, full material capacity will be used, and area under this curve will be calculated under USD. Just to let you know that what is the difference between elastic and plastic design. In plastic design, unlike USD or in ASD, plastic analysis is carried out in order to find the behavior of the structure near collapse loads. So target is actually to identify the collapse mechanism. In this type of design, material strength is taken from inelastic range, and obviously in USD also we use the material strength, full material strength of concrete. However, the steel strength used is up to yield limit. It is observed that whether the failure in case of plastic design, actually the failure mechanism or capacity is calculated, and it is observed that whether failure is brittle or ductile, and most favorable failure mechanism will be the failure with lot of warning and energy absorbing before failure. So there are advantages of plastic design, but in design office practice and to make a new design, normally this plastic design is less preferred and ultimate strength design is practiced. However, when you want to explore the failure mechanism or capacity analysis is need to be carried out, then this plastic analysis and design will get importance. In PRC 1 and 2 as well, we will carry out not only the capacity analysis of a member, of a structural member, maybe a beam, a column, a slab, even a footing, but also to design them against the demand. So there is little difference in capacity review and design. In capacity review or analysis, you will be given with the size, shape, for example, a cross section, rectangular or circular. So geometry will be given to you. Each and every dimension of the cross section and length of the member will be provided to you. You will be given with the materials used in that member, steel and concrete, for example. You will be knowing what is the maximum FC prime or the maximum strength of the concrete and steel yield strength. And you will be asked then to tell how much load this member can carry. So the question is reverse, that this is the member with this dimension, this cross section and this length with these materials inside. Tell me how much load I can safely put on this structure. Maybe uniformly distributed load or point load. So the question will be that how much will be the capacity of this member. While in design, in direct design, question will be that there is a load uniformly distributed or point load, and based on that load there will be some movement and shear force or torsion, and you will be asked that against this load calculate how much cross section size is suitable and how much reinforcement steel bars inside will be provided to resist that demand, to resist that applied load which is causing movement and shear and in some cases torsion as well on that structural member. So both we will talk in detail in this subject. So you, at the end of this course, you will be able to determine not only the capacity but also the design of a new member against the demand you will be knowing. As a designer, you can make the difference by achieving economy and safety as well. So both are very important targets, objectives of the designer, not only to achieve safety but also economy. So economical structures are always preferred. So there is one journal statement given that economy is always inversely proportional to self weight. Very much valid statement for steel structures, because steel cost you can very easily relate with the weight of the steel member. More steel weight, more will be the cost. Even when you will purchase the steel from the market, your unit cost will be with relationship of per kg weight of the steel. Even in concrete structures, more self weight means more big footing size to transfer that load to the soil underneath. More self weight means it will attract more seismic forces, because F is equal to ma. So more lateral forces, once it will be subjected to a heavier structure, it means more steel and more cost will be involved. If we are talking about the reinforced concrete structures. So always you want to get more smart structures. You want to reduce self weight, and two main objectives, safety and economy, are important. Here in this subject, we will discuss design of structural members against two load cases, dead and live load. Both are static gravity loads, and hence two combinations which combine these two load cases, dead and live, will get more importance. And out of different combinations, just one second, combination may govern that your movement or shear force demand will get bigger value as compared to the first combination, 1.2 dead plus 1.6 live. So both of the combinations you will check, and out of them which will give you highest demand, maximum demand, will be used for the design of the structural member. And in ultimate stand design, as I said earlier, that factor of safety will appear on both sides of the equations. So actually keep in mind that this 1.2 and 1.6 in combination 1 and 1.4 in combination 2 is actually factor of safety on action side, on demand side. While On the resistance side, we said that factor of safety will be in denominator, and once we take reciprocal of it, it will become less than 1. So that factor of safety which will be present on the resistance side, and Greek letter phi was used on the resistance side with nominal resistance phi mn or phi vn or phi pn. That phi will get value zero point 0.9 when flexure or bending moment resistance will be the design task. Even in case of direct tension, the reduction only required will be 10%. So zero point 0.9 will be the factor. So that also reflects the confidence, consistency in test results that the reduction hardly required is 10% on the capacity. While if you compare this bending or flexure with shear and torsion, the reduction required is 25% on capacity. So factor of safety is bigger as compared to reduction. So this factor of safety also reflects how much confidence we have in our predictions, and also on the type of failure. So the shear or torsion failure will be brittle, will be sudden, less consistency in test results, or little doubtful predictions will make this reduction little more stringent. So this is 0.75 applied in columns, compression members, columns with ties which is less ductile as compared with column with spirals. So is the reduction required in capacity. So there is a difference in the reduction factors. So column will be our topic in PRC2. I mentioned in my previous lecture that you can't eliminate shrinkage from concrete because you will add water in concrete to hydrate the cement particles. So surplus water, once it will evaporate, it will result into reduction in the volume of the concrete. So that shrinkage is unavoidable. However, you can minimize it by lowering the water cement ratio. Less water, good curing can reduce the shrinkage, but you can't eliminate it. And coefficient of shrinkage is summarized underneath at various ages, which can be multiplied with the length to estimate the shrinkage. So just for your reference, values are given and you can use them to predict the shrinkage at various ages, 28 days, 3 months, or 12 months. Excessive shrinkage can be avoided by proper curing during the first 28 days because almost half of the total shrinkage takes place during this period. So I may say that first 7 days are even more critical after casting. So you must be very careful at site and implement proper curing scheme at site. Creep which is a slow deformation of material over considerable length of time, maybe over a span of years, 7+ years, at a constant stress or load. So this change in length with time at sustained loads, you can't eliminate from concrete. However, this specific creep summarized in this table will reflect that when you have a higher compressive strength in concrete, specific creep will reduce. So with 21 megapascal, if it is 145 into 10 raised power minus 6 per megapascal, so it will reduce to 58 into 10 raised power minus 6 per megapascal when strength will increase from 21 to 55. So this again, this for your reference, this specific creep given here can be used to estimate the change in length due to creep. And on next slide, a simple example is given where you will find that on a 3 meter long column on which self weight of the building is sustained for several years and concrete in that column is of 28 megapascal compressive strength. However, the sustained load due to self weight is hardly 10 megapascal for the last several years. So from that table, we can select that what will be the specific creep against 28 megapascal FC prime. The value on previous slide selected is 116 into 10 power minus 6 per MPa, and then once we multiply it with the stress, sustained stress, we will get the strain, sustained stress into specific creep, which is per megapascal given, will give us strain, and that strain multiplied with the length of the member, change in length over original length is actually the strain. So the strain multiplied with the length will give us the change in length, and for this column which is 3 meter tall and under several years of sustained stress of 10 megapascal, it shortened to about 3.5 millimeter. So this can give you a rough assessment that how detrimental a creep can be in reinforced concrete members under sustained loads. So this shortening can obviously increase the stress on the steel bars, and in this way, this should be considered while designing the structural members. So rest of the slides already have been discussed in the video lecture, so please go through them. So in next lecture, I will quickly go through the rest of them, and then we will discuss ultimate and design topic. So few of the slides are with reference to your lab part. So please watch the recorded video to understand these introduction slides. So in next week, we will have 2 hour lecture with from my side, because next week we will swap 1 hour with 2 hour. So in next, I will be starting the ultimate stand design, and we can spend few minutes on these remaining slides as well. So if you have any question, you can post me on this team PRC1 section B. So I am going to stop the recording at the moment. 39 students are online, and 40 are online, and if you have any question, you can excuse me, there is a load chat. Okay, no problem. In our area since morning both is almost no problem. We can understand the issues of connection, and that's the reason recordings are also available, and moreover you can text me anytime on this MS team. Some valid questions I will respond, inshallah, no problem. Okay, take care. Allah Hafiz. If you want to say something, you can unmute your mic. CR.
No, sir, it's okay.
Nothing. Okay, then this recording is being uploaded, so you can watch that video in the Teams folder of PRC. Sorry, PRC section B. This one in files folder, and in recordings it is being uploaded. Okay, then Allah Hafiz.